Okay, give me a second. Okay, so it is a matter of great pleasure to introduce my dear friend, Dr. Chiranjeev Mondal. He is a pleasant personality and is going to entertain you for some time now. So, formally, he did his BSc and MSc from Calcutta University, Kolkata. After that, he joined PhD in Saha Institute of Nuclear Physics, where he worked on constraining the density dependence of symmetry energy using mean field models. During this work, he published several physical review papers and others. He is currently working as a postdoctoral fellow in University of Barcelona. In his today's talk, which is entitled as Finite Nuclei to Neutron Stars and the Theory Caught in Between, he will be highlighting the importance of nuclear ingredients from finite nuclei description to the massive neutron stars, as the title says. Uh, with these words, I would now like to welcome Dr. Chiranjeev for his talk. Dr. Chiranjeev, please, you
Okay.
can start.
The first time somebody called me doctor, so that gives me something new to look at. Good afternoon from Barcelona, because I think we are in different parts of the day in different places. So let me just start. I'll be talking about today the finite nuclei to neutron stars and the theory caught in between. The title is probably too heavy to justify with my knowledge, but I have tried to incorporate the few works I have been part of so far with the context of this title. I don't know how exactly it works, but if I hear somebody speaking, then I stop to hear your question, because I'll be happy to take your question in the middle of the talk rather than waiting for the end to come. So, what is exactly the problem we have in hand? At one side, we have atomic nucleus, and the other side, we have neutron stars, two massively different type of nuclear system, and we are trying to make a bridge between these two systems. And at first, it seemed kind of very improbable or impossible to make a bridge between these two massively different systems. But over the last decade or so, there has been some remarkable achievements in nuclear theory to make a nice bridge between atomic nucleus and neutron stars. And once this communication is started between these two massively different systems, we can establish theories more massively grounded on basic nuclear interaction. So what is the problem we are facing to go from these very tiny objects to these massive objects? Let me start by showing the mandatory figure we do in nuclear physics talk, the chart of atomic nuclei. I mean, in their own rights, all of these different nuclei, they are separate laboratories, if I may call them like that. But today in this talk, we are mainly interested in the gross properties of them. And if we look at the center of a nucleus, the density is something of the order of 2 into 10 to the power 14 gram per centimeter cube, and the radius associated with them are of the order of few Fermi. On the other extreme, apart from looking at these different structures of the neutron star, I'll come into this shell structure of neutron star in the later part of the talk. But right now, let us look into their gross properties. Typically, the radius of a neutron star is of the order of 10 kilometer, and the density goes at the center of the star as high as 10 to the power 15 gram per centimeter cube. So we are looking at these two different type of systems where the size differs of the order of 10 to the power 18, and the density also goes from at the center of the nuclei almost to 5 times at the center of the star. And we are trying to build a theory based on basic nuclear interaction. But unfortunately, even after 100 years of development of nuclear physics, we still do not know the exact nature of the force between two nucleons. And the best we have in the business is the is a quantum chromodynamics theory, which gives us the nature of the strong interaction, which governs the interaction between quarks and gluons, which are the building blocks of nuclei. But when we change from the quark-gluon degrees of freedom to the nuclear degrees of freedom, the QCD calculation on the lattice faces some tremendous problems, because when you make the lattice size really high, then the perturbative nature of the theory does not work anymore, and you need to develop a physics to describe the properties of finite nuclei, which is essentially a non-perturbative theory. So the next best thing we have in the business is no-core shell model. But even there, of course, I mean, last 10 years or so, there have been some remarkable achievements in this field, both in the QCD lattice and no-core shell model. But even with these very sophisticated theories, we could only go up to very small nuclei like calcium or so. Until recently, like last 5 years or so, there has been a tremendous development with chiral effective field theory, where under the chiral perturbation theory, one can expand the strong interaction in terms of some generic momentum. So if you take care of enough interactive figures, like if you go up to N3LO or so, you can basically explain the basic nuclear-nuclear interaction, even encountering the three nucleon force taking into account. But all these theories, which are primarily rooted into the basic nature of the force, they are supremely difficult and also computationally super expensive. I mean, even the smallest of nuclei take maybe days to calculate the basic binding energy property of a small nucleus. And we are in this talk basically interested in going up to the size of neutron star, where we have to even incorporate the theory of gravity juxtaposed with this basic nuclear-nuclear interaction. So right now, with these fundamental forces, it's, I should not say impossible, but right now, with the current computational facilities, there is no calculation available going from this to neutron star calculation. And the best hope we have in hand are the mean field models. The alternative approach of mean field models is also density functional approach, where you basically, instead of a potential formalism, we start with some energy density functional written in terms of the different densities constructed out of the wave function and their derivatives and so on. Even though the mean field models, I mean, they are not as fundamentally rooted like these three approaches I have told before, but with 8 to 10 parameters, they can explain properties running from finite nuclei to neutron stars quite fluently. I mean, if we can take into more correlation into account into those 8 to 10 parameters, we can do wonders with these mean field theories. And what we are essentially going to do now, that we use the mean field models and we look for nuclear matter properties, which is kind of a bridging building block between this density gap between finite nucleus and neutron star. Because at the core of the neutron star, the associated density is, as I showed you before, is something around 10 to the power 4 gram per centimeter cube, whereas at the core of the neutron star, this goes almost 5 times higher. So we need to grow some theory which can vary as a function of density, and that is exactly what we do with infinite nuclear matter. So what is infinite nuclear matter? It is a hypothetical conglomeration of infinite number of nucleons without any Coulomb force, without any surface, isotropic in nature, and we basically study nuclear matter properties in two extremes. One is the symmetric nuclear matter, where the neutron and proton densities are same, and if you plot the energy per particle for symmetric nuclear matter as a function of density, it saturates. That means it has a minimum at some density, which we call the saturation density, which is typically very close to the density at the center of any nucleus. In terms of natural units, translate to some 0.15 to 0.16 Fermi minus 3. And in our normal CGS unit, it goes to something like 2 into 10 to the power 4 gram per centimeter cube. Now, how do we characterize this symmetric nuclear matter? We define the energy per particle at saturation, which we call epsilon 0. The first derivative vanishes because it has a minimum here. So the next derivative, which appears in the Taylor's expansion of the energy per particle, is the second derivative of energy per particle with respect to density, which we also know as the incompressibility coefficient. There is also another quantity which quantifies the density dependence of the force we are encountering as the effective mass of nucleon existing in the system. At the other extreme, we study the pure neutron matter, where the matter is formed only of neutrons, and essentially all the natural systems, starting from any nuclei to neutron star, the asymmetry lies in between, where basically the neutron density is a bit higher than proton density, but mostly it's lying in between these two situations. So we need to define a kind of difference between a symmetric system and an asymmetric system, and that is exactly what we quantify as the symmetry energy by taking the energy per particle difference between the energy per particle of pure neutron matter from the energy per particle of symmetric nuclear matter. Now this is a function of density, which you can also expand around the saturation density, and we get different quantities like symmetry energy at saturation, its first derivative, which we call the slope parameter, or the second derivative, which we also call sometimes the symmetry incompressibility. Now, by some means, if we can quantify these several quantities which I have just shown before, or I'm showing right now, then we can understand the density dependence of the nuclear theory in general. But as I said before, that this is a hypothetical system, we cannot measure them directly into any laboratory. So we need to connect these quantities to real experimental observables, which we can measure in some laboratory or confirmed by some astrophysical observation, for example, observables of neutron star. Then only we can constrain them, and then we can quantify or even structure the basic symmetries of the nuclear theory. And that is exactly what is done. Binding energy of nuclei, which is one of the best known quantity in nuclear physics, or if I may say, basically one of the best known quantities in physics, I mean precisely known quantities. With the binding energies of nuclei, one can know about the energy per particle of symmetric nuclear matter, which is known to be something around minus 16 MeV. The charge radii of nuclei, which is also quite well measured in laboratories, can give us the idea about the saturation density, that is the order of density at the center of the nucleus, which goes as 0.15 to 0.16 Fermi minus 3, or something around 2.4 10 to the power 14 gram per centimeter cube. The giant monopole resonance of spherical nuclei, which is basically the breathing mode of nuclei, where the nucleus expands and deflates around its center. This kind of excitation energy can give us the idea about the compressibility. As you can notice, that compressibility means that how well you can squeeze a nucleus, and this mode of excitation can give us the idea about the incompressibility. And right now, the incompressibility is known to be lying around 230 MeV or so. Now, binding energies of asymmetric nuclei also can give us the quantification of the symmetry energy at saturation, which is of the order of 32 Fermi. The effective mass of nucleon in symmetric nuclear matter can also be quantified by the help of isoscalar quadrupole resonance or from the help of maximum mass of neutron star, which has been one of the primary revelation in the astrophysical observation. The current, I'm
I
sorry.
think Chiranjeev, you are not talking about error bar in any place. You're just saying this is equal to 230.
Yes, because we are not talking about error bars right now, because I mean, I'm not trying to quantify them exactly. I'm trying to give the outlook of the subject here, that how we know some gross properties, but here we are not really interested in very specific numbers. I'm just trying to give some idea that how we try to connect experimental quantities to theoretical quantities.
Okay.
Because as you can see, I mean, here I'm not specifying the effective mass very precisely, because it's not precise as precise as the ones I have shown before. This is exactly what I'm coming into. Because when you develop some theory, you need to specify, of course, errors. But here we are not exactly trying to pinpoint what should be their value, or trying to apply those values in some more development. We are just
I'm talking about experimental point of view.
Yes.
Yeah.
Can you ask me the question again?
No. For example, this compressibility.
Yeah.
This is 240 plus minus 20.
Yeah.
So I am talking about experimental point of view.
The thing is that, I mean, you know it very well that in even in nuclear measurements, like in experiments, I mean, most of the experiments are influenced also by the theory governed behind it, right?
Yes.
So sometimes when you translate something in terms of 240 plus minus, they do not exactly measure this quantity K0. They measure something called K delta, which is kind of the finite nuclear equivalent of this quantity, and that translates into 240 something. But if you do with a separate set of nucleus, instead of what you are telling probably is from 10 isotopes.
Yes.
So if you incorporate 10 isotopes, then that 240 becomes 210 or even 200 sometimes. I mean, in nuclear physics, nothing is for certain. I mean, when you are quantifying, especially these nuclear matter properties, it depends on what is the underlying theory you are using to explain that quantity. Isn't that so?
Yes.
But right now, I am not interested in that kind of specific numbers for these quantities. I'm just giving some gross outlook how one can find out these numbers from experiments.
Okay.
So moving on, but the symmetry energy parameters, the slope parameter and the symmetry incompressibility, I mean, their estimates are not as precise as the ones for these other cases. So one of the primary studies to quantify the value of L was done by relating neutron skin thickness of a heavy nucleus, which is defined as the difference between root mean square radius of neutron distribution and root mean square of proton distribution inside a heavy nucleus as a function of the slope parameter L in a macroscopic droplet model. And later on, those quantities, the neutron skin was calculated for 208 lead, and correspondingly from the same model, if you calculate the value of L from several models, and if you plot them, they were found to be related to each other. The correlation coefficient is almost kind of 1. So the idea behind this kind of correlation studies is that this skin thickness being an experimental quantity, if you can measure from some experiment very precise value of those quantities, you can, I mean, momentarily pinpoint the value of L just from looking at this graph. But the problem of measuring neutron skin thickness is that it involves measuring the radius of neutron distribution inside the nucleus. Neutron being a charged neutral particle, the conventional electromagnetic probes does not work very well. So you need to incorporate probes which are based on strong interaction. And the strong interaction itself being not very precisely known. So you introduce a lot of model dependence in your measurement itself just to find the value of neutron skin.
Chiranjeev,
Yes?
I have a question. I
Yes.
understand this plot the correlation between neutron skin thickness and L with different models.
Yes.
Okay. So if I want to correlate experimental values
Yeah.
like delta R and P with L, whether correlation will be perfect or not?
Because I don't know exactly what whether I understand your question properly,
So
but
the question is, I
no.
can again.
Let me get to that. As you said yourself that you need to have several models to plot this kind of correlation,
Yes, that I
right?
understand.
But when you are doing an experiment, you are measuring it for only once.
Yeah.
So you are basically trying to prove one of these points through your experiment.
So yeah.
And your experiment will come with some error bar in the y-axis.
Yes.
Yes?
Yeah.
That's it. From experiment, that's it.
Sometimes L in L case also error.
What?
For slope parameter,
Yeah.
sometimes precisely not measure, means precisely not, because this is also comes through the nuclear matter calculation. So
Yeah. Okay. I understand your question now. Okay. So from your experiment, you will have some error from on the measurement of your neutron skin thickness. So
yes.
that error will be in the y-axis. Now, the building theory behind it, from which you have constructed this line, you can see there is this brown region, which is kind of your 90% confidence limit and 90% prediction band. There is a gray bar you can see.
Mm-hmm.
So you put your experimental constant in the y-axis here. Yes.
Mm-hmm.
You will probe, like if you plot a vertical line for, let me show you here. If you probe a vertical line here, for example this, which translates from this to this, that translates into the error bar on L as a green line.
No, that I understand. You can put experimental value and to just try to percent the skin thickness with the help of nuclear model. But
Yep.
I am asking different thing.
Yeah.
If you have this experimental data points in the case of lead 208,
Yeah.
let us say this is by Prex experiment.
Yeah.
This neutron skin thickness. You have all other experiment done by other labs that is
Yeah.
related to also lead 208. So if you put all these neutron skin experimental data and corresponding the L values,
Yeah.
then can we see the correlation?
Okay.
I don't want to use this all these model.
Okay. You want to put the different experimental points and you want to know whether there is a correlation or not.
Yes.
I have no idea because I have never thought in the direction. But what kind of physics you want to extract from there? You will not get any physical information from that graph. Apart from some y equals to mx plus c line, what more you will extract from that line? Because using that, if you are going to use some different technique in the next measurement you are going to do, how are you going to use that information in the next experiment? I don't see any. I
Chiranjeev,
don't see. Yeah.
I understand
actually,
this
see,
plot very precisely. I know all these correlation paths, but I want to
ha,
understand experimental point of view, not
ha,
theoretical point of view.
Chiranjeev,
Because you
Yes.
have already a large number of experimental data points in the case of neutron skin thickness. Prex experiment, other experimental labs also give neutron skin thickness data.
Chiranjeev,
Yes.
see that experimentally you will get only the value of skin.
Yeah. That's what I. No. No. What he's asking is
Uh,
that if you plot those different measurements on a plot, single plot,
hmm.
L versus skin, and of course, we suppose that there is a correlation. If you kind of see that they are kind of correlated to each other, you will of course obtain the line like this, what we do for theoretical models. But how is that going to help for the next measurements you are going to make?
No, but when you measure the experiment
Yeah.
from the different lab, you will get only the value of skin.
Yes.
Yes.
You will not get the value of L from the lab.
From the lab, I mean, from the lab, of course, you are not going to get any value of L. For that you have to use the line I am showing right now.
Yes.
Exactly. So, I mean, what kind of correlation Bharat is asking, I couldn't understand. Bharat.
I also do not understand. So that's what I'm saying. That
so,
line.
So along x-axis, this is also experimental line. This green one.
No. This is where things get blurry. Yeah. See, the L is a purely theoretical quantity which is defined inside nuclear matter.
No, what is your green points are showing then in the x-axis?
The x-axis is some estimate
the
from a
bar.
yeah. So here the line in the x-axis, you can call it experimental, the error on L, but it is extracted from this line. The measurement you have done, or you can do in a laboratory, is the one which you see in the y-axis. That y-axis translated into this x-axis from this line.
By using the theory, basically.
By using the theory line, the blue line.
I got your point. I got your point now.
Okay.
So.
Okay.
Yeah.
This line only tells you that how can you correlate between something which is measurable with something which is not measurable.
Yeah. So basically, the L information is coming from this line only.
Yes, exactly.
For the experimental paper.
Yeah, L is not accessible in the lab.
Yes.
Okay.
This is the benefit of this correlation, actually.
Exactly.
Yes.
This is a kind of calibration curve, you can say.
Yeah.
Chiranjeev, can I give my opinion?
Yes, please. You are the expert here.
Yeah. Okay. I am one of the authors of the figures, so in principle, yeah. There are few experiments that you can really measure the neutron skin thickness. There are different experiments of different nature. For instance, measuring a giant dipole resonance or any other thing that allows you estimate L. So in principle, what you know is more about the value, the possible experimental values of L, and from this correlation, you can estimate the values of the neutron skin thickness. The neutron skin thickness, unless that you measure directly the neutron skin, there are the experiments that we consider in our calculation were old measurements of the neutron skin performed by a Polish group. There is also this famous experiment PREX, but this famous experiment, the point was that really the things were not so nice and they could not extract the real value. The importance of PRX is that it's a measurement where you use basically weak interaction that is free of all the problems of a strong interaction. Yeah, this is the situation. I mean, measure directly the neutron skin thickness is complicated. Rather, what you estimate is the value of L, and from this graph you can estimate the values of R rather than the contrary. Yeah?
Okay, thank you.
So Javier has already introduced you to the PREX experiment, which I was going to bring just now.
Yeah, okay.
This is the only model independent probe. I mean, by model independent, I mean it does not involve the strong interaction. It's based on some parity violating electron scattering experiment. But the problem here again persists that the technical difficulties are immense, and the only measurement which are available to the public right now is having a very large error. As you can see, it's 0.33 plus 0.16 minus 0.18 Fermi. So with the current existing set of mean field models, you can basically fit this value very easily with any parameter. As you can see from here, that it translates into a wide range of L, which is from 35 to 135 MeV. So this is exactly what motivated us to look for alternative calculations, as Xavier pointed out before, that there are calculations also existing in the literature trying to constrain the value of skin thickness or even the value of L from giant dipole resonance or the dipole polarizability. We try to do it with binding energies of nuclei, and we noticed that if we involve the binding energies of really asymmetric nuclei, where the number of neutrons are twice to that of protons, for example 30 neon or 24 oxygen, and you take the difference of its symmetric partner, where you have equal number of neutrons and protons, and you calculate this binding energy difference from several models and also the neutron skin thickness of lead, and you plot, you can see that there is a correlation existing between this binding energy difference and the neutron skin thickness. If we really involve nuclei which are really asymmetric, and this kind of nuclei were never part of the fit when when the parameters of our mean field models were obtained. So this kind of gave us a motivation to obtain one model where we feed the binding energies and charge area with some standard nuclei which are usually used in the literature. But on top of them, we added the binding energies of these nuclei which I have just shown, like 24 oxygen or 30 neon. And also on top of that, we had 36 magnesium, which is having 12 protons, or 58 calcium, whose binding energy is, whose existence is experimentally confirmed very recently, 56 calcium and 58 calcium. And we added their binding energies into the fit and we obtained the model. And there we could see that within some error analysis technique, that the value of L can be constrained really tightly. So with this, I stop discussion on the value of L. With these different probes available right now, for example, dipole resonance or this calculation I have just shown, or there are other calculations also, the value of L is believed to be lying between 40 to 60 MeV right now. Of course, one needs some exact kind of assurance from real experiment like PREX2 or something. Until that happens in future, it's believed within the different domain of nuclear theory that the value of L lies between 40 to 60 MeV. But the situation is not so nice if we go one more derivative higher, which is the symmetry incompressibility. The value pretty much varies in the literature from minus 200 MeV to plus 200 MeV. That's a huge error bar. And we tried to find a reasonable estimate of that quantity starting from some non-relativistic model, and where you could see that we can write an expression for this symmetry incompressibility in terms of its lower order derivatives, the symmetry energy at saturation and the slope parameter, and involving some other symmetric nuclear matter properties like Fermi energy or effective mass and so on. So if we believe, of course there is a matter of some uncertainty even with these isoscalar properties like effective mass, but that is nowhere in comparison with the value of symmetry incompressibility in the discussion. So if we kind of accept that they are much more constant than this quantity in the left hand side, so we can idealize this equation as a very simplistic equation where you can write the symmetry incompressibility as a function of the difference between 3 times symmetry energy from the slope parameter, and try to see whether this actually exists in the existing models in the literature. And we have seen here that starting from almost 500 different mean field models, both relativistic and non-relativistic, that this correlation actually exists, and the correlation coefficient is very close to 1. So the idea is that now the J is known to be something around 32 MeV. If we believe that the value of L is something varying from 40 to 60 MeV, we can give a very good estimate of symmetry incompressibility, which is something around -112 with an error bar of 71 MeV within the present calculation. Now in a different calculation, we have separately pointed out these black points which correspond to scum models, how one can obtain this kind of expressions, which we did in a very general feature. We have shown that very explicitly in the scum interaction how these kind of relations arrive. Even though this trend is followed by RMF models, that is the relativistic mean field models, till date there is no analytical justification behind this kind of correlation in relativistic mean field models. Maybe there is possibility to explore relativistic mean field model why this kind of correlation exists, because the prediction was initially from a non-relativistic framework, but we have seen that this is followed even by the relativistic mean field models. So far so good for concerning the different nuclear metal properties. But what more we can do? And now that this is some exciting time looking at all different types of experimental observables coming on, and as I said before, that the mean field model we use, not only what we use and what everybody uses, you have to incorporate as many correlations as possible, because this is not completely fundamental in the sense that it is not based on nuclear-nuclear interaction. So there is some possibility that you might miss some correlation in your theory, which you have to incorporate taking into account as many different type of observables as you can. So that was one of our goals recently, and as we know that the maximum mass of neutron star plays a very crucial role nowadays to validate any mean field model. If you want to validate your mean field model or any model to work for a domain of density, you need to obtain maximum mass of neutron star, which has to be more than 2 solar mass. Also, after 2017, August 2017, this gross tidal deformability, which is the kind of measurement of the wave patterns formed by the tidal field when two massive stars merge with each other, and that can be quantified by this tidal deformability, and from the experiment they have given some constant on those quantity. So the theories you produce nowadays has to follow these constants given by the experiments. And also on top of that, one should take care of the excitation energies in nuclei, like centroid energy of giant monopole resonance, or peak energy of giant dipole resonance, or the dipole polarizability. And that is exactly what we were trying to explore in a recent calculation. Let me come to a proper explanation of this figure. So we have identified 22 different non-relativistic scum models, which are kind of very successful models believed to be in the literature, because they can explain a lot of different types of nuclear metal properties and nuclear properties, or even the properties of neutron star. So we categorize them on the basis of their effective mass value, effective mass of nucleon value. The red ones, for them, the value of effective mass lies between 0.6 to 0.65. For the blue ones, it varies from 0.65 to 0.75, and the green ones varies from 0.75 to 1. The red line denotes the lower limit of the maximum mass of neutron star one should achieve. So the moment you plot this bound on the lower limit of the maximum mass of neutron star, you see these models mostly with green color, that is their effective mass lies between 0.75 to 1, they are kind of ruled out. And on top of that, if we now impose the experimental bounds on the centroid energy of giant monopole resonance for 208 lead, you can see that now even the red lines, the red dots are ruled out, which says that the effective mass should be very, very small, that is from 0.6 to 0.65. Now on top of that, after incorporating the constant on centroid energy of GMR, if we also impose the constant on the peak energy of giant dipole resonance, you can see that now only these two models they survive all these states of these tests of different constants we have implied. And now on top of that, if we impose the dipole polarizability of 208 lead, it basically comes down to only these two models lying here, this two yellow triangle, which pass all the different experimental constants we have put on here. And now if we calculate the tidal deformability or tidal deformability from these two models, which kind of respects what is provided by the present scenario given by the experiments. You can see that for both of them, the tidal deformability, which is given in the x-axis, lies way below 500, which is a dimensionless quantity. So this kind of gave us a motivation to construct one SCUM model where we fit the binding energies of standard nuclei, their charge radii, and these all different kinds of experimental quantities like centroid energy of GMR or peak energy of GTR or the dipole polarizability, also taking into account the maximum mass of neutron star to be 2 solar mass or more than 2 solar mass. We can see that we obtain with that model the tidal deformability are well within the experimental limit what is currently known. So even though it's kind of not understood exactly from the theoretical point of view why this kind of relation should exist between a quantity which is existing in a very small system like finite nuclei to a system like neutron star, but they exist. I mean, we have to understand them more rigorously in future maybe, but they exist. That is what it seems from both the constant point of view and also from obtaining a model point of view.
I think I have some question here.
Yes, please.
So the effective mass ratio when 0.75 to 1,
Yeah.
all these models are ruled out, right? According to the deformability, like less than 800.
Yeah.
Okay. So the only surviving is the 0.6 to 0.75, right?
Yes.
Or mass. But if I see the points in the red point, only few model.
Yeah.
Yeah. Right.
Yeah.
So because of this, the error in this parameter is large, or I don't understand. This 267 plus minus 144.
Yeah.
Which means the lower limit is very less. So
Yeah, but from the tidal deformability like GW 170817, there is no lower limit.
Yes, in GW17, lower limit is 70.
70, okay.
Yeah.
So how far it goes?
In your case, even just like
it goes something like 130?
Yes. This much
I think
lower
it's still
limit
within bound.
you can get. This is a surprise.
No, I still don't understand your question. I mean, if the lower limit is, yeah?
So in this parameter set, in this lambda 267.
Yeah.
So till now, as far I know that none of the SCUM model can reach up to that limit, means 120 or 130.
This can. This is also a SCUM model, so this can.
This is also a SCUM model.
Yeah.
But
this is the point. This is the point of making this model, because as you can see that the most of the models which are based on solely on giant monopole resonance or giant dipole resonance, they predict the effective mass always on the higher side. So
yes, That I understand. Recently, another paper came on that topic.
Yeah.
30 marks.
So
They have also found
to respect the bound on the tidal deformability, you cannot go just high up in the effective mass. That's what the point of making this new model. One of the main points was this.
Okay.
I mean, this is what I just told, that I mean there is no, I mean even we don't know exactly why these kind of constants, I mean, work with each other, like one property which exists in a massive set of stars, and the other one is kind of the excitation mode of a terrestrial nucleus. Why this kind of relation should exist between them, or there is a communication between them, we don't know the exact analytical reasons behind them, but so far numerically it shows that they are there. I mean, we should investigate more on this in this direction. But yes, as you pointed out earlier, that there are not many scum models which can go as low as this value in the tidal deformability. That is true.
Okay.
And that is why, as I told you, that this mean field models, they are not fundamental in terms of nuclear interaction. So if there is a new type of observable which is available, your model might have missed that when you obtain the parameters. So you need to always keep check on the parameters. If there is a new kind of observable available, you need to check your theory to validate that in your model.
So how about the maximum mass in this case, in this model?
Maximum mass, I think, I don't remember exactly. I think Professor Agrawal can tell you. It definitely
more than 2 m solar. It is more
How
than
much?
2 m solar.
It's
More than 2 m solar.
Okay, okay.
So should I move on?
Okay, okay. Move on.
Okay. So what next? What more we can do? Of course, we can, as I told you, as I pointed out maybe several times, that we need to keep check on the parameters and try to incorporate more and more correlation into the system or in your theory. What more we can do? From the experimental point of view, this is a very exciting time, because now that all these different experimental facilities available all throughout the world, there are more and more really extremely asymmetric nuclei are being discovered near the neutron dip line. As I told you earlier, this 56 or 58 calcium has been discovered very recently in this year. Also, there is a kind of hint found that 78 nickel, which is a kind of very holy nucleus for theoreticians, because it has magic figures both in the number of neutrons and protons. It is also found to be, I mean, kind of evidence has been found to exist. And also there is super heavy elements which kind of open up with their observation, new kind of physics can open up in the nuclear interaction sector. And as Professor Vinius has pointed out before, that the Prex experiment, which measures the neutron skin thickness of lead without any hindrance from the strong interaction, there is a proposed experiment coming up very soon. It should have been done by now, but there are some very technical difficulties hindering the process, but they are going to do it in very soon. So they promise that the neutron skin thickness will be coated within some very tight constant. So that can give us some strong idea about the isobacter nature of the interaction. Also this year, there was a heavier neutron star was observed, which is more than 2.1 solar mass, which is something around 2.17 solar mass. And in future, I mean, from the gravitational, sorry, not gravitational, the general relativity point of approach, I mean, the maximum mass of neutron star can go up to 3 solar mass also. But of course, there is no observation yet. But if more and more massive neutron stars are observed, there will be necessary to check your theory that whether you are being able to reach that kind of mass or not. And now more than ever this year, LIGO is again under under run now, and they are almost discovering 1 or 2 events every other week. And probably recently, a month ago or so, there was also an event which was detected, which is a merger between a black hole and a supermassive neutron star. And one of the more exciting experiment is NICER, which kind of promises that they will measure the radius of a neutron star for which the masses are already known. This is going to be a revelation in the field, because even if the masses are still better known than the radii can vary from 10 to 15 kilometers for neutron star very easily, and that can translate into your isobacter part of the interaction a huge error. So if NICER can give the precise measurements of radii on different neutron stars for which the masses are already known, that will open up new theoretical frontiers, I think. So what are the theoretical techniques which are exciting and to be pursued in the future? Of course, there is this neural network, because as we do not know the exact nature of nuclear-nuclear interaction, we can use this sophisticated statistical tool where you can train your model, possibly a mean field model, and training your model with all sorts of different kind of data which are available, already measured in the experiments or from observation, and then you can use those neural network techniques to predict new quantities in the experiments. And also now that the more and more sophisticated computation techniques are available, one can go with the no-code shell model or the QCD lattice, really higher bigger systems. So now that even quantum computations are on the kind of horizon to appear very soon, available for scientific techniques, with those heavy computations, who knows, we can go with these ab initio calculations to even lead in future. And the other frontier, which I am going to discuss in the next part of the talk, is unifying the equation of state of neutron star. Because in all this scenario, what I have not discussed so far, that the neutron star also has a very distinctive structure. If we go from outside of a neutron star, you can see that there is a very thin atmosphere of few meters, and then you encounter outer crust where the density varies from 10 to the power 1 to 10 to the power 10. Then you encounter the inner crust when more and more neutrons drift from your nuclei, which are known to exist in the terrestrial condition, and forming a kind of neutron gas medium where the different nuclei float to densities of the order of normal nuclear density, and from there onwards to the core, the density goes as high as 5 times to the density of normal nuclei. From the different theories, by theories I mean mainly here the mean field theories, the core of the neutron star is essentially to be understood in the form of neutrons, protons, and electrons and muons in beta equilibrium. So that part of the theory is quite well understood, even from or relatively well understood from the theories of infinite nuclear matter. But the inner crust, which is kind of an exotic phase, where you have a background neutron gas, and really asymmetric nuclei are immersed in that system. And just before transiting into core, there might be also possibilities of pasta phase, where you have neutron droplets immersed in the nuclear medium. And from the radius point of view, the crust can go as high as even 1.5 kilometers if you like. So it almost consists of 5 to 10% of your total radius of a neutron star. So if we do not constant that very precisely, when these experiments like NICER provide you the radius of neutron star, there will be ambiguities to explain what is going on. And also in the binary star mergers, this is the kind of medium which can provide you content for rapid neutron capture processes. So by the time the two stars merge, the medium from this part of the star can give you possible site for our process detection. So it is not only necessary to know the structure of the system, I mean not only the overall structure of the whole star, but it is also necessary to know the structure of this layer of the star. And that is exactly what we have been trying for last 1 year or so, using the finite range non-relativistic Goni force. Before going
L
into
is also important for the inner crust calculation, slope of the symmetry energy.
Is that so?
Yeah, because many people are correlated with this L with the crust thickness. So
okay.
if L is large, which means the inner crust is very thick. If L is small, the inner crust is thin. So the neutron star cooling is very fast. Means L is small means.
Because very naively, even if I talk about the transition density between the crust and the core, the density associated here is of the order of 0.06, 0.07 Fermi minus 3, right?
Yeah.
And the quantity L is quantified at normal nuclear density. I think Professor Agrawal published one article where they have tried to correlate the value of L with the transition density, and they did not find exact correlation, so they kind of combined several other properties, and then only they could find correlation. So if I don't know this kind of calculation where they have tried to correlate inner crust thickness. Yes.
Yeah. I can explain you about something about this, huh?
Yes, please.
Yes, of course you can correlate the transition density or even the pressure density, transition density, with the slope of the symmetry energy. Although that this is not the only quantity that enters in the game, although that is maybe the most important one. There are other things. However, if you take a family of models, if you take a family of models where you can fix all the properties of the nuclear matter except the slope of the symmetry energy, you can find almost a very nice linear correlation between the transition density and the slope of the symmetry energy. Yeah, in such a way that low values of L implies high transition density, and by the contrary, if you go to very high,
so it's a negative correlation.
A negative, yeah, an anti-correlation, if you wish.
Yeah. Okay. But do you know this kind of calculation where they have tried to correlate the width of the inner crust with slope parameter? I am not aware of this kind of calculation.
Yeah. You can also do such kind. You can also do such kind of things to measure or estimate, rather, not really measure, to really estimate global properties of the crust, and by global properties of the crust, I mean radius and mass of the crust with the slope of the symmetry energy. There is this paper. Also, I wrote a paper about this. This is this paper with Claudia, and it is Physical Review 98 or 99. There we have explained several things of this, but this doesn't enter on on the structure of the crust, only in global properties of the crust. And global properties, I mean mass of the crust, size of the crust, and moment of inertia of the crust.
Okay.
Yes, yes.
Yeah, such kind of things you can correlate and can see how they works with L.
Okay. Okay.
Actually, what happens is if the L is large, the transient density will be small and the crust will be thinner.
Yeah.
Yeah.
So, as Professor Javier said, the entire thickness of the crust can be correlated with L, but I am not aware
Okay.
about only the inner crust thickness.
Okay. No, basically I mean this is the other point of unifying the equation of state, that you obtain the theory of the core with your model, and then most of the time it is either polytropic fit or some previously explained crust description, and you try to kind of merge them with some polytrope, and then you explain the maximum mass or the radius of the star. This is the general calculation existing mostly in the literature. But when we are talking about merging of stars or the possible source of possible site for our process, then it's not only the global properties which are important, but you also need to confirm the kind of structure, I mean the kind of structure they consist of, what kind of systems they are made of, or what kind of nuclei they consist of. That information is also very important, where you need to use the same theory what you have used for the core part. You have to build some consistent theory for the crust as well. So this is also one of the point of making unified equation of state. Okay. So with this, let me just give a very brief overview of the Goni force, where we have this density dependent part exactly like a scum force with the usual spin orbit part, but the zero range part of the interaction is replaced by an exponential, which is basically two different ranges mu, one for the short range and one for the long range. And there are this D1 family of Goni forces which are available. They are extremely good explaining the finite nuclear properties. But all those models, they were never used before for calculation of neutron star. None of them could reproduce the two solar mass for the maximum mass. So until very recently, Javier and his collaborators here, they have obtained a new Goni interaction called D1M star, where they kept the basic isoscalar properties of D1M interaction, which is extremely good for explaining finite nuclear properties. So they kept the isoscalar properties like D1M, and they refitted the L parameters, and they now produce one interaction based on this finite range force to reproduce the maximum mass of neutron star to be two solar mass. Now, this force may play some very crucial roles in the crust, because being finite range in nature, the pairing interaction can be taken into account within the same form as a mean field, which is not really the case in the zero range forces. So that is one of the advantages, goes in favor of this Goni force. So we use this D1M star interaction to study the structure of the inner crust of neutron star in the Wigner-Seitz approximation. Now what we essentially do, we take a box like we do in a finite nuclear calculation. We take a box, we fix the number of protons from before, and then we fill in with neutrons and electrons to find a beta equilibrium condition, and then we fill the whole box with constant electron gas. So with this, we construct the energy for several configurations and study for a given average density. So here you can see that the density range, the average density of the crust running from 10 to the power minus 4 to 10 to the power minus 2. And first here I plot, I mean here at the left, I mean all these different dots, they represent the number of protons. So at the leftmost point the number of protons is 14, and on the rightmost point the number of protons is 54, and all of them are corresponding to the separate Wigner size calculation in beta equilibrium configuration. And if you plot for a given average density for several configurations, you can plot these kind of graphs for different densities. So first we did a semi-classical calculation with pure Thomas Fermi nature, and you can see that it kind of attains minimum somewhere around here in most of the cases. Now if we add the h square contribution to the energy on top of this, the overall nature of the curves don't change much, but there is a shift of energy per particle overall for all these different cases. Now what we wanted to study, the quantal effects like shell correction or pairing on top of this, and the moment you add shell correction on this configuration, then you can see the distinct minima appear in the structure. For example, this higher average density, the minimum appears at z equals to 40, whereas for lower average density, where the conditions are very much like finite nucleus, you can see the minimum appears at 50, and you can find local minimum at 20 or 28, which are known to be the shell closure places for finite nuclei. So we also added pairing on top of this, which does not change the overall minimum position, but they regulate the overall energy per particle throughout the whole structure. So now, for example, if I only concentrate on this average density 0.06, you can see that for a given average density of inner crust, if it is 0.06, the configuration of that particular cell would be z equals to 40 with the corresponding number of neutrons, which I remember to be around thousands or so. And the size of the Wigner size box will be something in between 16 and 17 Fermi. And if we look at the density distribution, you can see that the size of the box is here 17 Fermi, and the nature of the density for neutron is denoted by the black lines, and the red one by the for the proton distribution inside the Wigner size cell. I mean, if you go lower average density like 4 into 10 to the power minus 4, the box becomes really large, but the density is very similar. I mean, the nature of the density is very similar to that of finite nucleus. But the moment you go in higher in density, if you reach this kind of density, you can see that the density saturates at not at zero value, but a non-zero value. This is what we call the neutron gas, which is existing in the background.
I think I have a doubt. So
Yes, please.
at the center, every nucleus has the same density in each place. At R equal to 0. RWS equal to 0.
Yeah. Not exactly same.
You can see this 40 to 50.
Yeah.
It's 0.095 or something.
No. I mean, this is naturally obtained. I mean, we did not force any external force to obtain that value. So essentially, what you do, you consider that for this given number of z, you find the equilibrium configuration, which is given by equating the chemical potential of neutron to be equal to the summation of chemical potential of proton and electron. Okay, so in that condition you obtain this configuration where the number of neutrons are also fraction here. I mean, if you force to be the number of neutrons also whole number as proton, it may not be exactly the same value, but okay, I mean that is not going to change the result very much. So that essentially determines what kind of density, because we have taken some Fermi distribution, so that's why the nature of the distribution is very similar to all cases, but what value it should take, it essentially comes from the beta equilibrium condition.
Okay, go ahead.
I mean, it looks very similar to those of finite nuclei, only with the exception that here you have this this saturation of the density at non-zero value. This is very unique. I mean, this is what constructs the background neutron gas in the system.
Porque yo estoy ahí.
Yeah?
Ahora he salido.
So, in terms of the potential of the system, this is also very similar to those of finite nucleus. If we go to really small density, which mimics the condition of terrestrial conditions more and more, you can see that the potential has very similar nature to those exist in finite nucleus, but they become distinctly different, saturating at non-zero value or not going to zero at asymptotic limit as they do in the finite nuclei. Now all this information, now if we gather, like here the configuration is given by z equals to 50 and the corresponding neutron number. So we know the density, this, and the corresponding energy per particle. We can form the equation of state for crust using a same model for which we have also constructed the core part, and we have done some very preliminary calculation where I should only point out here the black line and the red line, which are of concern here in this talk, that the black line was originally published with the original D1 introduction, where the crust part was obtained with polytropic fit. You can see as far as the maximum mass is concerned, both of the black line and the red line, which is obtained with this distinctive inner crust calculation. The inner crust is the equation of the inner crust is given by the present calculation. You can see that the maximum mass is pretty much the same. The only difference appears at the lower mass part. So as we know that the crust consists only the lower density part of the equation of state, these two graphs become different only at the lower mass, making the radius a little bit different. I mean, this is very preliminary calculation, but you can get the idea.
How about the transition density between core crust in your case? Transition density.
Wait. Here we are essentially devoted to do the crust part. Okay, so you do this calculation with weakness side cell with your crust. Sorry, I mean you do the calculation of your crust with this weakness size approximation. The formalism I have just explained. Now you do your core part the way you do your beta equilibrated nuclear matter. Now you approach from both the sides. You go high in up density from this weakness size calculation, and you go down in your nuclear matter, beta equilibrated nuclear matter calculation from the high density side. Now there will be some density at which either of the configuration will give you less energy. You accept that. And Professor Vinius has been part of some dynamical method where you can smoothly transform from one kind of calculation of the crust to the calculation of the core. You do this transition smoothly by some dynamical method or thermodynamical method. So essentially the fact is that you accept the the energy per particle where it is less in the intermediate density.
Okay.
Yeah, there is this is the things are maybe not so simple. I mean, to do the calculation from the crust side and reach nuclear matter is complicated. You can see all these graphs and all this technology for getting such kind of things. In practice, it's much simpler to proceed in the opposite way and look in the uniform system at which density the system is unstable against formation of clusters. And this is what gives you the transition density. Typically, if you take only nuclear matter, is the so-called thermodynamical method. You can also incorporate finite range effects, and then you have this so-called dynamical method that gives you smaller transition density. So, of course, this is probably the best way to determine the transition density, but it's also difficult to reach this density from the crash site. And the reason basically is that in these cases, the size of the Wigner size cell is so small that maybe the conditions of applicability of Wigner size approximation fails. So it's a little bit complicated. I mean, so you can estimate, for instance, up to 0.06, and then from 0.06, I think that the transition density for D1M star is something like 0.08 or 85 or something like that. Then, okay, you interpolate between one and another. Notice that, however, the contribution of the crash to the equation of state is actually small. And the effects you can note maybe in very, very small neutron stars, maybe of half solar mass or something like that. For the maximum mass of the neutron star, what you do in the crash is practically irrelevant.
Yes.
Is not affected. I mean, you can do whatever you want. That is basically determined by the core. So.
Yeah.
So as I told before, as far as the maximum mass is concerned, these two different technology does not give much difference, but there might be some considerable difference in the radius for lower mass stars. But more importantly, these calculations are important from the structure point of view, that what inner crust is made of. I mean, we are thinking of even in future to do this process of unification in more general way, even going for the outer crust calculation with the same force. So that's pretty much it. As I said, I will not I will not have any conclusions in today's talk. So before ending, I want to thank all my collaborators with whom I have done the works I have shown today. But I will finish with a quote by Helen Keller, that the place between your comfort zone and your dream is where life takes place. And this is exactly where nuclear theory is right now. So we should consider ourselves very lucky to be part of this journey, and we should make most out of it. Thank you.
Okay.
I think nuclear theory is right now is a good place because of this LIGO and everything.
Yeah, it's exactly jumping in between without worrying anything about the world.
Yeah. Nice talk.
Yes, anybody has any other questions?
Hi, Chiranjeev.
Yes, please.
See, I want to make one comment. Like as you
Yes.
said that in the maximum mass, that no matter what you do, your crust result remain the same. Actually, see what happens.
No, no. What I said is that no matter what we have done, so I mean in this calculation with the crust, the maximum mass is kind of unaffected.
Even the radius also remain unaffected, right?
Yes.
Because as the mass goes up, the crust becomes thinner and thinner.
Yes. That's true. I mean
Yeah.
the effect of this calculation as far as the radius or the mass is concerned, if you are concerned about the radius of smaller mass star, then only this calculation makes some difference with these polytropic calculations.
Exactly, because the ratio of the basically, if you take the ratio of the crust thickness to the core radius, actually,
Yeah.
that goes up as you go down in mass.
Exactly, exactly. So I mean,
Uh, yeah,
if you notice this, the very last figure I have shown today, the difference between the black line and the red line, uh, there is considerable difference only when the mass is of the order of 0.5 to 1.
exactly,
By the
exactly,
time you reach more than one solar mass star,
exactly,
this
exactly,
difference is kind of zero.
exactly. Because that is why when you go up in the mass, all the dependent symmetry and energy, everything disappears because
Yes,
the
yes, yes.
crust
Yes, yes,
becomes
yes,
almost
yes.
thinner and thinner, actually.
Yes, yes, yes. But this
But
this might
I
play.
have
I
a
mean,
doubt here. But you are talking about point 0.5. But point 0.5 means the central density is somehow is large comparison to the if you're talking about crust.
but there are stars like this mass, no? Like not zero point 0.5, but definitely zero point 0.7 or zero point 0.8 solar mass neutron stars are there. I mean, in the catalog, if you look at, you will find stars like them. And this nicer experiment, which I told you before, they will not discriminate whether that mass of the star is 2 solar mass or 1.5 or 1.1. They will make their hands dirty whatever they can lay their hands on. So that's going to be important when you have these observations, because they cannot do observation by pinpointing the star from before. They will try to locate some stars which are more easily available, and they will try to measure the radius.
I think this data will release soon, maybe next month. They have done that.
Soon, maybe not before 2 years, because last time when I went to a conference, some people from NICER came, but all sophisticated experiments have their own difficulties.
Like Rex.
Exactly like friends. When I started my PhD, I had like 2018 will be the year Frex 2 will come out. We are touching 2020 now.
Yeah.
Yeah, I still want to add a comment about Prex. The problem with Prex was that they needed at least 5% accuracy in the measurement of the asymmetry in the cross section. Yeah.
Mm-hmm.
However, due to failures in the technique, they got 10% error, and this is the reason why you get this enormous
Error
range,
bar. Yeah.
this enormous error bar. We also estimate this is, well, it is nice to say this, that of course you could, theoretically, of course, if to measure L with an error of plus minus 10 MeV, but for to do that, you should measure the asymmetry with a 1%
Exactly.
accuracy that
Exactly.
probably is absolutely behind of the experimental possibilities. No,
Yeah,
this
yeah,
shows
okay, that's true.
clearly which is the limit of this.
Yeah, yeah. So this
Yeah.
fight will be on whose value of L is right in future.
Yeah, but if you measure this asymmetry with 1%, you get the L with 10%. You can see on this on this graph. Huh?
Yeah. Kind of 5 MeV corresponds to something like 0.05 or something.
Yeah.
0.01, sorry, 0.01 Fermi in the neutron skin thickness translates something like 5 MeV
5
in the
MeV, exactly. That's what we have noticed. Yes.
Yeah. The point is that really you are performing experiments of polarizing electron scattering, and you are looking for differences of 1 part in 1 million. So the possibilities are really, this is very complicated experiment, of course. Maybe with calcium 48 it could work, but we will see.
Okay, I think no more questions. Thanks, Chiranjeev, for nice talk.
You're welcome.
Okay, bye everybody.
Yes, bye Xavier. Bye. Good night.